Okay, in this video we're going to be looking at section 6.3, vectors in the plane. But before we start the lesson, let's do a little sort of warm up here. Got a couple points, 4, 6, 0, 2. Do we remember how to find the slope between those points and the distance between those points? All right, slope, remember slope is m equals, we subtract the y's, y2 minus y1, over subtract the x's, x2 minus x1. So I'm going to subtract in this order, y minus y, that's going to be a 6 minus 2, over top of a 4 minus 0. So that becomes 4 over 4, or slope of 1. Okay, and the distance. Remember the distance formula. Distance formula has a big old radical in it. And then underneath the radical are a couple of squared quantities added together. And in here we subtract the x's. So let's do same direction, 4 minus 0. And then here, 6 minus 2. 6 minus 2. So that would be the square root of 4 minus 0 is 4 squared. That's a 16. 6 minus 2 is also 4. 4 squared is another 16. So that would be the root of 32. Or we could write 32 as 16 times 2. And then that would be 4 roots of 2. So a couple of older concepts, slope and distance between points. These same ideas are going to be used here when we talk about vectors in the plane. So this is 6.3. Vectors in the plane, we got some bullet points. Represent vectors as directed line segments. Write component forms of vectors. Perform basic operations and represent vector operations graphically. Write vectors as linear combinations of unit vectors. Find the directional angles of vectors and use these to solve real-life problems. So what's the introduction say here? Quantities such as force and velocity involve both magnitude and direction and cannot be completely characterized by a single real number. To represent such a quantity, we can use a directed line segment shown in figure 6.10. Right here, initial point using the letter P, and then we go along here to the terminal point. We see the little arrow marks the terminal point Q. Remember in geometry we'd use the little ray mark there, the little arrow on top, PQ. We'll see later we can name this vector something like U, and that U is going to be bolded. The directed line segment PQ has initial point P, terminal point Q. Its magnitude or length is denoted like this. So here's PQ, and we've got sort of double absolute value bars there, and we've got the little arrow on top, the ray. So this is the magnitude or the length of the vector. So if we get a couple points, of course, we're going to be using the distance formula to find this magnitude or length. Okay. So two directed line segments that have the same magnitude and the same direction are equivalent vectors. For example, the directed line segments down here in figure 6.11 are all back here. These in figure 6.11, these are all equivalent. They're all the same length and they all have the same slope. We can sort of make out visually almost that they are parallel to each other and they are the same length. The set of all directed line segments that are equivalent to the directed line segment PQ is a vector V in the plane. Written as vector V is this ray from P to Q. Vectors are denoted by lowercase boldface letters. The most common you'll see are U, V, and W. So here in example 1, the directions show that vectors U and V are equivalent. So by the phrasing of the directions, we should get the affirmative when we do our algebraic check that these vectors U and V are equivalent. First, let's look at their magnitudes or their lengths. If the lengths are the same, they might be equivalent. So let's see here. We'll do the vector on the bottom first. This one here, U. Vector U, again, that's boldface. Its magnitude, that would be from P to Q. This vector U has the magnitude here. We're going to just use the distance formula. So I'm going to set up a big old radical. couple squared quantities underneath. And for this vector u, I've got 3, 2 and 0, 0. So if I subtract, my x's will be 3 minus 0, and my y's will be 2 minus 0. 3 minus 0, 2 minus 0. So this becomes the square root of 3 minus 0 is 3, and that squared is 9. 2 minus 0 is 2. Square that, you get a 4. So here we get a root of 13. That's for vector u. Vector v has a magnitude from r to s, initial point r, terminal point s. So we're up on these points here. Let me circle them in red. And there we're going to find that magnitude. Again, I'm just going to set up some empty parentheses here. I'm going to do 4 minus 2 and 4 minus 1. So 4 minus 1 for the x's, 4 minus 2 for the y's. 4 minus 1 is 3. You square that, you get a 9. 4 minus 2 is 2. You square that, you get a 4. Just like above, we're going to get a root 13. So the magnitude, the lengths of those vectors check out. We're halfway to making a statement that they are in fact equivalent. Now let's check out their directions or their slopes. So down here to vector u, we're going to find the slope of that. And remember, that's y minus y over x minus x. So my y's are going to be 2 minus 0. My x is 3 minus 0. And the direction of vector u is 2/3. Let's go on to v. So change in y's are up top, so that's going to be 4 minus 2. Downstairs are the x's, 4 minus 1. 4 minus 2 is 2, 4 minus 1 is 3. The slopes are the same. So we can say that u and v are equivalent because we check their magnitude, their lengths, they're the same, and we check their slopes, and they are the same. Now here, component form of a vector. The directed line segment whose initial point is the origin is often the most convenient representative of a set of equivalent directed line segments. This representative of vector v is in standard position. So standard position, initial point is at the origin. A vector whose initial point is the origin can be uniquely represented by the coordinates of its terminal point. So that would just be a point in the plane, an x and a y coordinate, or here v sub 1 comma v sub 2. This is the component form of vector v, written as v equals, now notice these aren't parentheses, these are sort of like a little sort of bracket. So vector v is v sub 1 comma v sub 2. The coordinates v sub 1 and v sub 2 are the components of vector v. If both the initial point and the terminal point are at the origin, then v is the 0 vector, and it's denoted by 0 or 0 comma 0, again in those sort of brackets. So in the box we have our official definition, component form of a vector. The component form of the vector with initial point p, p1 comma p2, and terminal point q, q1, q2, is given by. So here's our ray, p to q. So we got our bracket, q1 minus p1, comma, q2 minus p2. And then we do that subtraction and we get our v sub 1 and v sub 2. That is the component form of vector v. The magnitude or length of this vector v is given by, we're going to subtract just like we did up here, square it, plus subtract just like we did up here and square it. So that's just, we could take these forms here in these brackets, this v1 and v2, we can just square those, add them up, and put them under a radical. If the magnitude of v is equal to 1, then v is a unit vector. A unit circle has a radius of 1. Here, the unit vector has a magnitude of 1. Moreover, if the magnitude is 0, if and only if v is the 0 vector. And then below it says two vectors u and v are equal if u1 and v1 are the same, and u2 and v2 are the same. For instance, in that first example, the vector from u from the origin to 3 comma 2, that would be 3 minus 0 comma 2 minus 0, or 3 comma 2. The vector from r point r 1 comma 2 to point s for 4 is the same thing, 3 comma 2. So the vectors u and v from example 1 are equal. Example 2, finding the component form of a vector. Find the component form and the magnitude of vector v that has this initial point. Let's graph it. 4, negative 7. So here's our initial point. Usually the book uses p for that. Terminal point, negative 1, 5. We'll use q for that. And then we can draw. Is this going to let me get... there it is. We can draw an arrow from P ending at Q. So there's our vector. Let's do a little work over here. So that first point, our initial point, 4 comma negative 7, that's our P1, P2. The terminal point, negative 1, 5, is our Q1, Q2. So to find our vector v, or excuse me, v sub 1, we're going to subtract Q1 minus P1, or negative 1 minus 4, which is negative 5. And then our v2, remember this is what's going in these little sort of brackets, negative 5 comma something. V2, we're going to do the same thing with the Q's, or the Q1 and the P1. So here, this is going to be the Q2 minus P2. So that'll be our 5 minus negative 7. 5 minus negative 7. Add the opposite. That'll turn into a 12. Negative 5, comma 12. Again, that's in our brackets there. So that is our component form. So find the component form and the magnitude. Now the magnitude, again, sort of like this little shortcut here, the magnitude of that, we could do the distance formula, but we've kind of already done some of the legwork here. Now that we have this component form, let me get a little room up here, erase. We've got this component form, negative 5 comma 12. We can just put a radical here and a plus sign and square this. Negative 5 times negative 5 is 25. And square the 12. 12 times 12 is 144. If we add those, we get 169. And the square root of 169 is 13. Now let's look graphically what we did here. When we found this component form, negative 5 comma 12, if we're at initial point P, this is our movement left or right. So since this is negative, we're going to move to the left 5 units. 1, 2, 3, 4, 5. This is our movement up or down, so rise and run. But here now this is our rise, so 12, since it's positive, we're going to go up 12 units. To go from negative 7 to positive 5, we've gone 12 units. So we've done Pythagorean theorem here. This is 5 and 12. This was just Pythagorean theorem to find our hypotenuse, 13. That is our vector here, our directed line segment. We found the length of it. Couple for you to try here to check points. So pause the video, try these problems. Either listen to my solutions or go to the online book, and you can get the solution there in English or Spanish. Okay, let's make this one here kind of quick. Yeah, let's do the distance formula first, I guess. We've got vector u from the origin. We've got vector v up above. Each of these are going to have radicals with some squared quantities underneath. Let's see here. The first one, v. Let's do the x's 5 minus 2, and then the y's are 3 minus 2. 5 minus 2, 3 minus 2. So this is going to become a 3 squared plus a 1 squared. That'll be a root of 10. Down here, the lower vector, ooh, I guess I did that backwards. This we just did here is v. So this will be u. X is 3 minus 0, y is 1 minus 0. 3 minus 0, 1 minus 0. So that becomes a 3 squared and a 1 squared, just like above. That's going to add up to a 10. So the magnitudes are the same. Let's check the slopes. Oops. There's my eraser. Slope for v, up top, change in y's are up top, so the y change will be 3 minus 2 over the x's 5 minus 2. So that'll be a 1 upstairs and a 3 downstairs. For u, our change in y is 1 minus 0. Denominator, the x change is 3 minus 0, so that's also 1/3. Slopes are the same, or directions are the same, and the magnitudes are the same also. So those vectors are equivalent. Oops. So yeah, this one, just like the last example there, component form and find its magnitude. So let's see here, we've got our initial point being negative 2, 3. We've got our terminal point being negative 7, 9. So here, again, we're sort of doing, there we go. So our x value here, we're going to subtract. Remember, it's always a terminal minus initial. So this is going to be, let me switch to red ink, negative 7 minus negative 2. Negative 7 minus a negative 2, that'll turn to a plus. We add that and get a negative 5. And now here again, when we subtract in the proper order, this will be 9 minus 3. 9 minus 3, that's 6. So here is our component form. And now if we want to find the magnitude of that vector, I think there we have vector v. If we want to find the magnitude of v, we can just put a radical here. And then first square this. Negative 5 squared is 25. Square this, 36. Add those together, you get the root of 61, which cannot be simplified any farther. Okay, some vector operations here. Two basic operations are scalar multiplication and vector addition. In operations with vectors, numbers are usually referred to as scalars, so scalar multiplication. We're just going to multiply through by a constant. In this text, scalars will always be real numbers, no imaginaries. Geometrically, the product of a vector v with a scalar k is the vector that is the absolute value of k times as long as v. When k is positive, k times v has the same direction of the vector as v. When k is negative, we're going to take an opposite direction, as we can see here in the figure. Oops, let me move this out of the way. So here's vector v. Its direction is up and to the right, and its length, its magnitude is this long. Half of v, we would just cut that vector's length in half. The direction is the same. 2 times v, we would double the length of the vector. And I cut some off. There's the rest of it there. So 2 times v, we would double the vector. Negative v, multiplying this by negative 1, it just reverses direction. Now it's headed in the opposite direction. And here's negative 3/2. We've lengthened it by a factor of 1/2, and we've switched its direction. To add two vectors u and v geometrically, first position them without changing the lengths or direction so that the initial point of the second vector v coincides with the terminal point of the first vector u. The sum u plus v is the vector formed by joining the initial point of that first vector with the terminal point of the second vector as shown in the figure. Where is that? The technique is called the parallelogram law for vector addition because that vector u plus v is often called the resultant of vector addition, is the diagonal of the parallelogram. So let's see here. We've got these two vectors u and v. Here's u. If we put v on the end of it, if we take, let me see if I can pull this off here in red. If I take this vector v and I just move it up here and put it on the end, here's my u plus v. This vector becomes u plus v. We're starting the initial point of u and going to the terminal point of v. Now, another way to pull this off, if I had left v alone, I could put, here's vector v, and then I'll take this other vector here. This was u, or no, this was also v, and this one was u. So that's why they call it the parallelogram law. Here's u and v, here's u and v. So this is u plus v up here. Down here would be v plus u. But adding is commutative, so we're going to get this same resultant vector here in the middle anyway. So in our box, we got definitions. U is u1, u2. V is v1, v2. Again, these are not points. These are vectors. Let them be vectors and let k be some scalar, a real number. The sum of u and v is just this. Add the u1 and the v1, add the u2 and the v2, and that is your sum. Scalar multiple, you just multiply that scalar multiple k times whatever was already in those brackets. All right, so let's try this out. Let v be this, negative 2, 5. W is a vector 3, 4. Find each of these. So for letter A, 2 times v, so we're going to have 2, and we're going to multiply it by this vector, negative 2, 5, and it's just this easy. Distribute the 2, negative 4, 10. And that is our new vector, 2 times vector v. B. We're going to subtract. Order is important, so here's vector w. I'm going to write it like this, 3, 4. And we are going to subtract vector v, negative 2, 5. Now, if you want, we can distribute the negative and then add. So if we distribute here, this will turn into a plus 2, and we can add those and get 5. If we don't distribute, that would just be 3 minus a negative 2. My pen's getting a little wonky here. Distribute the negative here, so this will be a negative 5. 4 minus 5 is negative 1. So there's our new vector. Letter C, we got a little bit of both going on here. V plus 2w. So v, that is negative 2, 5. And then we're going to add 2 times w. 2 times w is 3, 4. Order of operation says we should multiply first. So let's distribute that 2. Now it's going to be 6, 8 plus this vector, negative 2, 5. Now we just add the vectors here in the first position. Negative 2 plus 6 is 4. Plus 5 plus 8 is 13. Oops. 4, 13. There we go. There's our resultant vector. I think we can see these graphically. That's what I got hidden over here. So the first one, 2 times v. This is vector v. We just doubled it. So now its length is twice as long. B is w minus v, or you could think about this as w plus negative v. So here's our w vector, 3, 4, and then negative v is going to take us in the opposite direction, so it takes us down this way. So here's our the answer that we found for part B. And the last one, v plus 2w's. So here's our v vector, and then here's w, but it's twice as long now, 2w, and that takes us to our 4, 13. We got some properties here. U and v are vectors, uv and w are vectors, c and d are just scalars. Those are just real numbers then. The properties listed below are true. Just like you can add 2 numbers together, you can reverse the order and you'll still get the same answer. Adding is commutative. Here's our associative property, u plus v plus w. We can add the u and v first and then the w, or we can add the v and w first and then the u. Doesn't matter, the end result is the same. We can take a vector and add the 0 vector to it, and it doesn't change anything. We can take a vector and add to it its negative sort of reciprocal there, its negative counterpart, and you'll get the 0 vector. Remember, multiplication is also commutative, so we can multiply the d times the vector first and then c, or we can multiply the two scalars and then multiply that by the vector at the end. Here's just sort of the distributive property. We can distribute vector u to scalar c, and then vector u to also scalar d. Here, sort of the reverse of that, we can distribute a scalar to two vectors. 1 times anything leaves it alone. 0 times anything is 0. So here, if you multiply a vector by 1, it doesn't change anything. It's still the same vector. Multiply any vector by 0, you get the 0 vector. This last one is pretty handy for simplifying answers. So this is magnitude, the magnitude of scalar c times vector v. We can, and you'll see how this makes our computations much simpler, pull out that c value here as long as we absolute value it. Leave vector v in there, that's its magnitude, its length, but pull out that c and put it in absolute value bars. And that is going to come in real handy on this example here. U is 1, 3, V is negative 2, 5. Find the magnitude of each scalar multiple. Now here, this is the more inefficient way to do it. 2 times U. So we're going to, let me back that up. We're going to take this vector U here, I'll underline it in red, 1, 3, and we're going to multiply it by 2. So that would be 2, 6. Now, if I want to find the magnitude of that, that would be square root of, square that, you get a 4. Square the 6, you get a 36. 4 plus 36 is 40. And then we could simplify that into 4 times 10, or 2 roots of 10. Now, if we use this property here, it makes the work much easier. This 2, the magnitude of 2 times u, is the same thing as the absolute of 2 times the magnitude of u. Now, 2, the absolute value of 2, is just 2. And we're going to multiply that by the magnitude of u. Remember, the shortcut for magnitude, just put a radical here and square this. 1 squared is 1. 3 squared is 9. 1 plus 9 is 10. Same answer that we got here. Oops, there we go. B, negative 5 times u, find the magnitude of that. So we're going to apply that property again. Oops, there's my ink. That would be the magnitude of negative 5 times u is going to be the same thing as the absolute of negative 5 times the magnitude of u. The absolute of negative 5 is 5. And now the magnitude of vector u, that's this one right here, square the first thing, 1 squared is 1. Square the second thing, 3 squared is 9. 1 plus 9 is 10. 5 root 10. Last one, letter C. Now we finally use vector v. 3v, find the magnitude of that. So we're going to pull out the 3, take the absolute value of it, that's just 3, and now we're going to do the magnitude of vector v. So square the first thing, negative 2 squared is 4. Square the second thing, 5 squared is 25. So that becomes 3 roots of 29. All right, a couple here for you to practice, and then that'll be it for this video. So pause, try these out, and then start it back up to check your answers, or check them on the online book. Okay, A, u plus v. So we're going to add, for the u part, or the first part here, it's going to be 1 plus 3, that's 4. For the v component, 4 plus 2 is 6. For part B, subtract. We're going to subtract them now in this order. 1 minus 3 is negative 2. 4 minus 2 is 2. Now for part C, we're going to have to multiply by scalars first. So 2u, so I'm going to double the things in here, so that's going to be 2 comma 8. 2 comma 8. And then we're going to subtract 3 times this vector. So if I multiply each of these by 3, 9 comma 6. Now I subtract 2 minus 9 is negative 7. 8 minus 6 is 2. All right, the first one here, let's pull out that 3. So that's going to be 3 times the magnitude of u, and that's just 3. We're going to put a radical there with a plus sign under it. For the u vector, we're going to square each of those, 16 and 1. So that becomes 3 roots of 17. For this one, pull out the negative 2, absolute value that, so that's going to be 2 times vector v, or 2. We're going to square the stuff here. 3 squared and 2 squared, that'll be a 9 and a 4. 2 roots 13. Letter C, pull out the 5, absolute value it, and then here vector v. So we're going to square these numbers again, same as we had last time, 9 and 4. 5 root 13. All right, that's the end of the examples here. Again, these assignments are on WebAssign right now. So check those out. If you have any computer or WebAssign issues, you can do page 425 in the book, these questions. And I'll probably be making another video here shortly for these odd problems. If you're having trouble with the even ones, these odd ones are adjacent, so they're very similar. Checking out the odd problems can help understand the evens.